should be singing a duet.
Now that's a hazard.
Well, that will end things quick. Okay, so I'm going to talk a little bit about some of the two and the three-dimensional effects we can see at soft play sites, particularly when those soft play sites exist within a basin. And it's important to remember some of the things we talked about on the first day when we talked about one-dimensional analyses. They can be very useful within basins and outside of basins, but we need to recognize that when we do one-dimensional analyses, we're looking at vertically propagating SH waves, shear waves, horizontal particle motion. They are propagating perpendicular to a series of horizontal soil layers, and we assume that those layers extend infinitely to the left and infinitely to the right with constant properties. In reality, soils don't have constant properties. They vary spatially for a number of reasons. But if we make the assumption that they're constant everywhere, that can exaggerate or overemphasize certain characteristics of certain layers. For example, if we have a very soft layer and a very strong impedance contrast, we may start to develop extremely large strains in the soil at that level. And those strains can soften the soil substantially. And as it becomes softer, the impedance contrast between that layer and the underlying layer increases. And that causes more energy to be reflected back downward, which means less energy is going to be transmitted upward. And so we may underestimate the amount of shaking that's going up to the surface in a situation like that. We should also recognize that not all incoming waves are propagating vertically, so there will be other components of motion, and certainly there's going to be waves coming from other directions and different types of waves. And so the 1D analysis is an approximation of reality. It's a very useful approximation, but it doesn't capture every aspect of earthquake ground motions, even under conditions that are likely very close to one-dimensional. So we often have to perform multi-dimensional site response analyses, and there could be a number of reasons why we would do this. And one of the most important of which is the presence of an alluvial basin, particularly when the alluvial basin is filled in with soft soils, or soils that are much softer than the materials underneath them. And these basins can have different dimensions that range from tens of meters, maybe in a river valley, a small river is passing through, to many kilometers, such as the basin that we have here, and the basin that exists near where I live. We'll also have multidimensional analyses from variations in surface topography that can be important in certain areas. We have multidimensional analyses that can be required for man-made structures, such as dams and embankments or structures. But if we look at alluvial basins, they can come in many sizes and shapes, many widths, many depths. We typically have a softer material underlain by a stiffer material. And as waves propagate upward, even just vertically propagating shear waves are going to be refracted when they hit boundaries between different materials, and we'll see a focusing of the energy. And that focusing can occur in a local area and cause increased levels of shaking in that area. In Seattle, we have a basin, the Seattle Basin, and the basin effects had never been measured, but they were recognized even back in 70 years ago in the 1949 earthquake. At the edges of the basin, houses had extensive damage to chimneys. So in these areas, the chimneys of the houses, the unreinforced brick chimneys, all fell over. And in other areas they didn't. It wasn't understood very well why that would happen at that time. And now we know that basin effects contributed to that. There's a couple cases that are useful to consider. If we have on the left a flat soil layer with a lower velocity, when a wave comes up and hits that boundary, it's going to be refracted to a more vertical position. and it's going to hit the ground surface, and it's going to be reflected back downward. And if it reflects downward with an angle that's relatively steep, less than the critical angle of refraction, both reflection and refraction are going to occur, and some of the energy is going to be transmitted down underneath to the material underneath, the stiffer material, and be removed from the soil layer. And that causes the wave that bounces back and forth to have its energy decrease over time and decrease relatively quickly. If we have a wave coming in and hitting the edge of a basin, the inclined edge of a basin, the transmitted wave is going to come through at a flatter angle. It will be reflected off the surface and come back down at a flatter angle. And if that angle is greater than a critical angle of reflection, then none of this leakage of energy, this transmission that we see in the flat layer case, is going to take place. And all of that energy gets reflected back up and trapped within that softer layer. And that can lead to an increased level of response in a basin, particularly near the edge of the basin, because as it travels across the basin, damping will reduce its amplitude. We can also have surface waves developing near the edges of the basin due to the interaction of the incoming waves with that free surface. So this trapped energy can increase the length of the ground motion. And we see that very commonly in basins that we have longer duration ground motions. There are some examples just from an analytical investigation where a wave comes in to a flat layer, is refracted up to a steeper angle, and if it's measured, if the wave is measured at different locations, then we see that it has a waveform that looks something like this. When the same wave comes up and hits the edge of an inclined basin, the side of a basin, then at each of the different locations, we see outside or at the edge of the basin, we see just the single pulse that was applied. But as we move further into the basin, we see that the amplitudes have increased, and we also see that the duration has increased. And so we see this, it's common to see this duration lengthening occurring within basins. We can have basins that are directly above faults, or we can have basins that are offset away from faults. If the basin is coincident with the fault, we see nearly vertical wave propagation. If the basin is wide, as Professor Gray has said, it may be appropriate to use one-dimensional site response analyses to account for the stratigraphy of the soils and make reasonable predictions of the response. If the waves are coming in from the side, this is when we can see surface waves and trapped waves causing increased durations and increased amplitudes. So we talk sometimes about coincident basin locations and distinct basin locations, where this location of the fault is distinct or separate from the location of the basin. We often use some depth, the depth to some limiting shear wave velocity in our ground motion models to at least approximate the effects of a basin or the existence of a basin. Whether it's 1 kilometer per second, 1.5 or 2.5 kilometers per second, they tend to take that role and they increase the response at longer periods. So period-dependent basin amplification factors are available for both of these cases, and they have effects mostly on longer periods, to increase amplitudes at longer periods. If we do even some simple numerical simulations, putting in a simple Ricker pulse to a basin profile that looks like this, obviously rotated 90 degrees outside the basin, we see just a single pulse occurring with a certain amplitude. But if we look inside the basin, we see multiple pulses, long duration. We see some amplification of the motions. As time proceeds, the amplitude dies down, but there's a pronounced increase in the duration of the motion due to these waves traveling across the basin, being reflected off the other side, coming back. We see constructive and destructive interference of the waves. Here at the center line, they tend to cancel each other out, out towards the edges, they add to each other. And it's well known that we get stronger ground motions near the edges of basins. Part of this is due to the surface waves, the formation of Rayleigh waves. Part of it is due to the trapping of waves within this layer. But it's important to recognize that those kinds of phenomena exist. So at the basin edges, we can have particularly strong shaking that a one-dimensional type of analysis is not going to capture. And so we need 2 or 3-dimensional analyses to capture these kinds of amplifications. And as I'll show you in a simulation that was done in the Pacific Northwest towards the end of this presentation, those can become significant. Here's the Santa Monica Basin. I showed this quickly earlier. Ground motions recorded in the Northridge earthquake outside the basin on relatively low amplitudes and relatively short durations compared with the ground motions that were measured inside of the basin. The basin exists because of the Santa Monica Fault that comes through here, but you can see certainly much stronger shaking and longer duration shaking inside the basin compared to outside the basin. So basin motions will typically have higher amplitudes, lower frequencies, and longer durations. The significance of the basin will be influenced by its shape. If we have a wide, shallow basin, we may be able to use one-dimensional analyses in the center. Professor Gray showed a 1-to-1 scale for the Mexico City Basin. It's very, very thin. And one-dimensional analyses have proven to explain many of the observations and ground motion recordings that existed there, at least out towards the center of the basin and away from the edges. But near the edges, we may have significant 2 or even 3-dimensional effects that can influence our response. If we have a deep, narrow basin, there may be no location where a one-dimensional analysis is appropriate. So we need to keep that in mind. If we look at the Bogota Basin, and some information that was sent to us, we see a geometry that looks something like this. This is an exaggerated geometry. We have 120 to 150 meters of soft soils, at least at this profile. But this distance is about 5 to 6 kilometers. And so there's a scaling ratio of about 40 to 1 here. If we make it 1 to 1, the basin looks like this. And we can see that it is flatter, but it's not as flat as Mexico City. And so the basin effects, these 2 and 3-dimensional effects, are likely to be more important here than they would be in a place like Mexico City. So here with equal scales, we see a significant difference in the geometry. In Mexico City, in their 1985 subduction earthquake, ground motions were recorded at a number of locations out toward the coast, close to the epicenter. The Campos record looked like this, peak velocity of 150 centimeters per second, moving farther inland over a considerable distance. The amplitude had decreased. High frequency components had been scattered and absorbed by the Earth's crust, so the motion was quite a bit weaker. We get up to the Yunnan site that we talked about the other day. Peak acceleration is quite a bit smaller, 35 gals, 35 centimeters per second squared. But if we go to the SCT site that was underlain by 30 meters of the soft clay, we have ground motions that were about 5 times stronger than that. There was strong amplification at many locations within Mexico City, some of which was related to the resonance that occurred between the incoming motions that had a period of about 2 seconds. They were relatively long period motions because of the absorption and the decay of the high frequency components by the time they reached Mexico City, the inland area. When the recorded motions were compared with motions that would be predicted by GMPEs, they were found to be considerably stronger. And so peak velocities, which are shown here, are expected to decay with distance there at a rate that looked about like this, but there was very strong amplification and the ground motions were much stronger than had been anticipated. Peak velocities correlate to longer periods or lower frequencies than peak acceleration values do. Peak accelerations correspond to confluence of ground motion in the 5 to 10 hertz range or so. Peak velocities are more like 1 hertz, or perhaps a little bit higher than that. And so longer period motions here by the basin were being amplified quite a bit relative to what had been anticipated. If we look at where the damage occurred, a lot of that damage occurred near the edges of the basin. Part of that was due to the resonance effects, part likely due to the formation of surface waves and the extended duration of the ground motions. There were, in 2017, 2 intraplane earthquakes that caused strong shaking in Mexico City, a magnitude 8.2 and a magnitude 7.1, and strong motion stations recorded high levels of amplification within the Mexico City basin there. And again, predictions, even with updated ground motion models, showed very strong levels of shaking at a number of locations within the Mexico City basin for these 2 records. So basin effects are important. It's important to understand how a basin is likely to behave. Response spectra in these areas showed strong shaking in the 1 to 2 second period range. And so this basin effect of amplifying long period or low frequency ground motions has been demonstrated in different basins around the world and different earthquakes. If we look at some of the time histories as they were recorded, there are a number of time histories that are shown here. If we look outside the basin in the green area, these bottom 2 accelerograms show relatively weak motions with relatively short durations. But as we move into the basin, we see that near the edges of the basins, on this side and this side, we have ground motions that have higher amplitudes and longer durations occurring. So we see stronger motions here in the thinner soils near the edges of the basin. And if we look out at the center of the basin, the motions are weaker again. So the basin edges are important, and understanding the response at basin edges is important in order to properly design structures in those areas. The differences in the durations from within the basin compared to outside the basin. So these effects show up over and over again when we have strong earthquakes in areas where we have basins and basin effects. They can be examined by a number of different procedures. Here we see in the top row amplification factors for spectral accelerations. We see HBSR ratios, horizontal and vertical spectral ratios, and we see at the bottom response spectra. And they're all showing increased long period motions and amplification of those long period motions within the basin areas. We have to consider the dimensionality if we're going to try to predict ground motions within basins. We have to recognize that some frequencies are of more interest than others. There may be high frequencies that we're not so interested in. If we're looking at basins and soft soils, such as the soft clays that we have here, we're going to have short wavelengths in those materials. If we're concerned about high frequencies, then we're going to have even shorter wavelengths. If we have short wavelengths, it's going to require that our numerical analyses use smaller elements, whether we're doing finite element or finite difference types of analyses. Smaller elements means we need more elements to model a given geometry. More elements mean we're dealing with bigger systems of equations. They may also require shorter time steps, depending on the way our analyses are done, the way we integrate in time. Shorter time steps mean more time steps to make our way through an earthquake ground motion, and so we end up with big systems of equations and lots of time steps, and they're very computationally demanding, particularly if we're going to try to do a three-dimensional analysis. We also have to think about a lot of the factors that Professor Bray mentioned. He talked about a lot of aspects of the behavior of soft soils, of soft clays, and they all apply for 2- and 3-dimensional cases just as much as they do for 1-dimensional cases. So grade effects, degradation, strength effects, all of those things need to be accounted for in a 2-dimensional analysis, the same way they would need to be handled in a 1-dimensional analysis. We have to particularly be concerned if we have soils that are soft and weak about the large strains that are going to cause the shear stress levels to approach or even reach the shear strength of the soil, because simple extensions of and extrapolations of low strain behavior from resident column tests to high strains doesn't necessarily match the strength of the soil, the actual strength that's going to be mobilized, and in general it won't. And so you need to make sure that your model, when you get out to large strains, is going to capture the strength of the soil reliably. If you have, as we have here, relatively soft soils at large depths, when the waves come up, there's going to be high shear strains induced at that interface between the similar underlying materials and the bottom of the soft soils. We have to pay attention to, if we have soft clays that are underlain by bedrock, we have to pay attention to weathering profiles in the bedrock, because a sharp, distinct boundary will behave differently in a site response analysis than a gradual boundary that may have evidence of some weathering occurring. And so it can be important to characterize the upper portion of the rock if it is directly underlying our layer. There are also issues with the damping of clays at very large strain levels. A lot of nonlinear site response analysis codes capture the unloading and reloading behavior by the Mazing criteria, where we take our original backbone curve and we expand it by a factor of 2, we move the origin to our reversal point, and we unload along a path that is the same as the backbone curve, but expanded by a factor of 2. That gives us an advantage and has a nice feature of providing closed hysteresis loops when we have symmetrical loading. But we find when we're able to model the low strain damping behavior reasonably well, at least for these kind of simplistic models that use that approach. But when we go out to large strains, the basic criteria can greatly overdamp the actual motion, the actual damping ratios that we see in the laboratory. And so that is a factor to take into consideration when you're evaluating the suitability of a particular model, whether 1-dimensional, 2- or 3-dimensional, for analyzing those types of problems. In the area where I live, we have a subduction zone, a Cascadia subduction zone. It's off the coast of Washington. It's well west of the city of Seattle, where most of the population in this area is. We've had a large project that has involved simulating magnitude 9 earthquakes out in the Cascadia subduction zone. And in doing so, some group of seismologists that we work with have created models of the entire Pacific Northwest. So it extends from the northern part of California up into the southern part of British Columbia in Canada. It extends out to the east about 200 kilometers or so. So it's an extremely large model. It's a linear model. We did it initially with finite difference analyses, and we switched over to finite element analyses. It all involves low strain behavior, low strain properties, because it is a linear analysis. But it shows that basin effects, 3-dimensional basin effects, can be accounted for by this type of very large analysis. One of our students made what I think is a very nice simulation here. The lower portion here is the northern part of California. Moving up to here, we're at the Seattle area is at about this location. So there, we'll see when the rupture proceeds, we're actually modeling the rupture in this process. We're modeling the waves as they travel along the path from the source to all of these sites. And we'll then see what the time histories look like at several locations. And so, get my cursor back. The rupture begins, we can see waves spreading out, and they're traveling out in all directions, some out into the ocean, some more inland, some up along the coast. You can see greater intensity in the direction of wave propagation, which confirms what Professor Gray has shown. You see the ground motions reaching different locations. When it reaches Seattle, we have a three-dimensional model of the Seattle Basin. There's several layers of rock that are softer as you move up towards the surface, and there are glacial sediments on the surface, and you can see the difference in the amplitudes of the motions, great degrees of amplification within the Seattle Basin. And you can also see significant differences in the duration of the ground motion. So these types of analyses can be performed. The fellow that does them up in our area is a fellow named Art Frankel. He's a seismologist from the U.S. Geological Survey. In Southern California, Rob Graves and others have models that can perform these types of analyses. And I don't know if seismologists in Colombia are doing this kind of modeling at this point. Okay, they can be very useful to understand how basins are going to affect the ground motions. So to summarize, we need multidimensional analyses to deal with a lot of natural features like basins and man-made features as well. Basins can produce surface waves, and that's what we see in the Seattle Basin in those simulations. When we look at them more closely, we see Rayleigh waves being developed and oscillating back and forth within the Seattle Basin. And motion within the basin becomes quite complicated because it's three-dimensional and waves are being reflected and refracted in many different directions. But we do see consistently increased amplitudes at longer periods. We get very complicated motions near the edges of basins, so we need to recognize that those can be important. So they have both kind of a stratigraphic amplification due to the soil profile and its stiffness, but also we have these surface waves that can be important. We can do linear, equivalent linear, and nonlinear, multidimensional analyses. Nonlinear, three-dimensional analyses are not very commonly performed, but equivalent linear and linear analysis can be performed and can provide us great insight into these kinds of things. So that's the end of that presentation. Professor Gray would like to come up and use this microphone.
Any questions?
La pregunta se sale un poco del tema, pero está relacionado con el tema de suelos blandos en Bogotá. Siempre me ha cuestionado el tema de cimentaciones profundas con pilotes en Bogotá, lo referente al comportamiento antesismo, en particular el tema de pérdida de resistencia al corte por deformación del suelo. No sé si nos puede hacer algún aporte basado en las experiencias de México o en otras partes del mundo. Gracias.
Are you asking about the effects that piles have on affecting the shear strain that the earthquake induces compared to what you get in a free field site?
On the contrary, the loss of strength due to the earthquake on the pipe. The strength degradation due to earthquake effect on pipes.
The behavior of the pipes. That something like
There is some problem. I'm not.
So when you get straining in the soft clay, you will get modulus reduction. And you're worried about how that might affect or interact with the pile
Yes.
performance?
La resistencia.
The strength.
When earthquake waves come up, they're propagating vertically, and there's a certain strain that's being induced in the soil. When the pile is oscillating, responding to that ground motion, it's moving relative to the pile, and it's causing strains in the soil, but it's a different form of loading. And so, while there may be some degradation of the stiffness of the soil due to some pore pressure generation in a clay, say normally consolidated clay, the nonlinearity is occurring by different mechanisms. And so the softening nonlinearity that's due to the wave propagation is not going to directly affect the nonlinearity that's due to this local interaction between the soil and the pile that's trying to move laterally. The stresses are being applied on different planes, so there will be some interaction, but I would not advise using the stiffnesses that come from the 1D, say a 1D site response analysis to control the PY stiffnesses of the springs or the lateral interaction. There are different mechanisms going on.
There is one concern that we had as reviewers of the Mexico City Airport was there was a report in 1985 where there was enough loading of the building onto the piles where the piles going back and forth generated enough pore pressure where there was some water came out along the interface between the soil and the pile, and there actually was some water coming out of the surface. There weren't many observations like that, but at least it's happened one time. And so we made the consultant do some laboratory testing and do some analysis to consider that. Because to me, that's one of the scariest things. If you're counting on the piles, and these were friction piles, to be able to take that, to resist the overturning moment, and you're getting some degradation along that interface because of water coming up along the pile, that's dangerous. But it's something that we need to study more because we have very little empirical evidence of this being an issue. Some people think it's fiction, but I see it in the report. So at least one or group of people saw this happen in '85.
Buenas tardes. Mi pregunta va enfocada hacia los modelos 2D. En condiciones en las que haya que hacer un modelo de respuesta 2D o 3D, ¿se tienen algunas verificaciones iniciales para, digamos, para ver si las respuestas que se están dando son lógicas, como se hacen las sugerencias con los modelos 1D?
Yes, there are a number of examples of basins of different sizes that have been instrumented. They're not necessarily as heavily instrumented as we would like, and particularly in Japan, there are a number of basins. Japan has a very extensive network of strong motion instruments. So when we were doing our work for the Seattle area, we also built models of several Japanese basins, subjected them to the motions that had been recorded outside of the basin, and calculated the response of those models of the soil profiles within the basin. And we looked at primarily matching the response spectrum. We found that our model was able to capture that behavior reasonably well. So that is in addition to looking at theoretical solutions and showing that we could match theoretical solutions, we looked at those basins, and it was primarily Japanese basins that had enough instrumentation to give us a good indication that we were modeling their behavior accurately.
On the Wellington rebuild of the harbor, the wharf facilities and the port of Wellington in New Zealand, Professor Jeff Martin, myself, Professor Trubnowski were involved. We also had Brendan Bradley and some very good seismologists in Boulder. We did not have confidence in the analytical solutions, and they were not going to go through and get calibrated and be confirmed by the time we had to make decisions. So we used empirical base and edge effect models to change the ground motions calculated from 1D response to capture that. So I think your point is very clear, is do not trust a model, especially if it's 3D, and always look at doing the calibrations if you have the time, what Professor Kramer mentioned, but very importantly, focus on the empirical evidence on base and edge and use those empirical factors. Another case is with vertical ground motions. We typically don't worry about vertical ground motions, but when people do calculate vertical motions, they normally get them wrong. And so 9 times out of 10, and I've been on consulting boards with other people, so this is not just my opinion, we prefer using empirical relationships between spectral acceleration for a vertical motion and a horizontal motion than trusting anyone's ability to propagate vertical motions or motions that have the vertical acceleration time histories of the ground.
Okay. We've got to go to the next one as well. So we're going to move now into issues of slope stability. And we'll talk first about some of the